You ever hear the legend about the temple with 3 giant poles and 64 solid gold discs? The story goes that a group of priests has been tasked with moving this entire stack from one pole to another, but they have to follow a very specific set of sacred rules. And the legend says that long before they can finish their task, the world will actually end. Well, today, we're going to unravel the mystery behind this puzzle. It's called the Tower of Hanoi, and see how a really simple, elegant idea from computer science can solve it. Okay, let's get into it. So here's the basic setup. You've got 3 poles. We'll call them the source, the auxiliary, which is just a temporary helper pole, and the destination. Now, on the source pole, there's a stack of discs, all different sizes, with the biggest one on the bottom and the smallest one right on top. And the goal? Simple. Move the entire stack over to the destination pole. But, and this is a big but, there are 2 crucial rules. First, you can only move 1 disc at a time. And second, you can never, ever place a larger disc on top of a smaller one. The rules are simple, right? But they make for a surprisingly tricky puzzle.
I mean, moving 3 or 4 discs by hand, yeah, you can probably figure that out. But what if you had 10 discs or 20? Or what about the 64 from the legend? How would you even begin to write a computer program, an algorithm, that could spit out the correct sequence of moves for any number of discs you throw at it? Now that is the real challenge we're going to tackle.
And the answer, the secret to cracking this, lies in a really powerful way of thinking called recursion. And please, don't let that name scare you off. It's not just some complicated programming jargon. It's a fundamental problem-solving strategy, and honestly, the Tower of Hanoi is its perfect poster child. So here's the main idea behind recursion. In plain English, to solve a really big, hard problem, you just assume you already have a magical helper who knows how to solve a slightly smaller version of the exact same problem. So for our puzzle, if we want to move a stack of n discs, all we have to do is figure out how to use our helper who already knows how to move n-1 discs. Trust me, this little mental shift, this little leap of faith, it makes all the difference. So once you adopt this recursive mindset, this seemingly impossible puzzle of moving a giant stack of discs, well, it just boils down to a beautifully simple 3-step algorithm. And here it is. This slide shows us the algorithm in what we call pseudocode. It's basically just a blueprint for the logic. Now, look closely at that function Tower Hanoi. The real magic is happening right there, inside its own definition, where it calls itself to solve the problem for disk 1. That right there is recursion in action. It's literally asking that imaginary helper we just talked about to do the heavy lifting with a smaller stack.
Okay, let's break down what that code is actually telling us to do. To move a whole stack of n discs from the source to the destination, we first just ask our recursive helper to move the top n-1 discs out of the way. That's step 1. Get them from the source to that temporary auxiliary pole. Now, with those smaller discs gone, the biggest disc on the bottom is free. So step 2 is one single, easy move. Take that largest disc and put it right on the destination pole. It's now exactly where it's supposed to be forever. And finally, step 3, we just call our helper one more time and ask it to move that stack of n-1 discs from the auxiliary pole right on top of the big one at the destination. And that's it. Boom. Problem solved.
This recursive tree is kind of like a map of the algorithm's thought process. You see, to solve that one big problem at the very top, it splits it into 2 smaller problems. And then each of those problems gets split into 2 even smaller ones, and so on and so on. It's this cascade that keeps going all the way down until the problem is so simple, just moving a single disk, that it can be solved instantly. Then all those simple solutions just build their way back up to solve the whole thing. Okay, so the algorithm is incredibly elegant. I think we can all agree on that. But is it efficient? I mean, the solution works, but at what cost? We really need to look at just how many moves this clever solution takes, because the answer, well, it's absolutely staggering. So, to figure out the total number of moves, let's call it m of n, we can just look back at our 3 steps. The number of moves to solve for n disks is just the number of moves it takes for n-1 disks, plus that one single move for the biggest disk, plus the number of moves for n-1 disks all over again. This gives us what's called a recurrence relation. M of n equals 2 times m of n-1 plus 1. And as you can see from the notes here, when you start substituting the formula back into itself over and over, a really clear pattern starts to emerge. And that pattern leads us to this final, unbelievably concise formula. The minimum number of moves required to solve the Tower of Hanoi with n disks is 2 to the power of n minus 1. So for 3 disks, that's 7 moves. For 5 disks, it's 31. But for the 64 golden disks from that ancient legend, that is over 18 quintillion moves. To put that in perspective, even if you made one move every single second, it would take you over 580 billion years to finish. So yeah, the legend was right. The world would almost certainly end first. This kind of explosive growth, where the workload basically doubles with every single disk you add, has a name. It's called exponential complexity. And it tells us something really important. While our algorithm is totally correct and super elegant, it becomes incredibly, impossibly slow for large problems. It's a perfect solution, but one with some pretty staggering practical limits. But you know, the Tower of Hanoi is so much more than just a clever puzzle. The strategy we use to solve it, it's one of the most important and powerful techniques in all of computer science. This technique is called divide and conquer, and as the definition here says, it's a top-down approach where you divide a problem into smaller pieces, you conquer those smaller pieces by solving them recursively, and then you combine all those little solutions to solve the original big problem. Does that sound familiar? It should. It is exactly what we just did with the Tower of Hanoi. This diagram just visualizes it perfectly. You have the three phases. First, you divide the main problem into smaller, more manageable subproblems. Then, you conquer each of those little pieces, usually recursively, until you have a solution for each one. And finally, you combine those individual solutions back together to solve the big problem you started with. For our tower, that combined step was just stacking the disks. For an algorithm that sorts a huge list of numbers, this step would be merging all the little sorted lists back into one big one. And this strategy is absolutely everywhere. Some of the most famous and efficient algorithms that power our digital world rely on divide and conquer. Things like merge sort, which is a super efficient way to sort data, or binary search, an incredibly fast way to find an item in a sorted list. Even really complex math, like multiplying giant matrices, can be optimized using this same approach. It's a fundamental tool in the computer science toolbox. So, in the end, the Tower of Hanoi teaches us a really profound lesson. A problem that seems impossibly complex on the surface can often be solved with a simple, beautiful strategy if we can just find the right way to break it down into smaller pieces. It kind of leaves you wondering, doesn't it? What other huge, impossible challenges that we face, whether it's in programming or just in life, are just sitting there, waiting for us to find that one crucial insight to divide and conquer them?